And that brings us to the end of the question paper. This was a rather easy question paper only. The questions were interesting. I would say the geometry was easy. I would say especially these two number theory questions were the interesting ones in this paper. And I also liked this question on polynomials. Hello everyone, I am Deepta Basak. I'm a first year undergrad at ISI Bangalore, and after quite some time, I'm back. And in this video, we are going to have a discussion on the UGB paper of the ISI Entrance 2017. So, without wasting any more time, let's start. We'll start with the first question. Got this. We'll start with the first question. The first question says that we have a sequence an that is defined like this. Sequence that is defined like this, and the initial value of the sequence is also given, that is the value of a1 is given to be 2. We have to show that for all natural numbers, for all positive integers n, an is a rational number with an odd denominator. So as is typical for questions like these, we'll use the principle of mathematical induction to prove this. So the proof by mathematical induction requires a base case. The base case is given to us. So if we look at n equals 1, this is just if we look at n equals 1, we have a1 equal to tan theta, which is 2, which you can see can be written as 2 by 1. And so it's easy to see that this is a rational number with an odd denominator. The denominator here is 1. So the base case is true. Base case is true. For our induction hypothesis, we assume that AK equals tan k theta satisfies the conditions of the question. That is, it is a rational number of the form p by q, where p and q are integers, q is not equal to 0, p and q are co-prime, and additionally q is odd. So this is our induction hypothesis. Now we look at the next term in the sequence, that is ak plus 1. This is tan k plus 1 of theta, which is tan k theta plus theta. Now we expand this. Tan k theta plus tan theta over 1 minus tan k theta tan theta. Now we substitute the values, and tan k theta is just p by q. Tan theta is given to be 1, and this is 2p by q, right? Just simplifying this gives us p plus 2q over q minus 2p, right? Now clearly this is a rational number, obviously, because p and q are integers, so this is a rational number. Moreover, we had assumed here that q is odd. So since q is odd and 2p is even, this term in the denominator is basically odd. So ak plus 1, this term also satisfies the conditions of the question. This is a rational number with an odd denominator. Hence, by the principle of mathematical induction, we can finally conclude that an is a rational number with an odd denominator. For all positive integers n. Sorry. So this was the question, right? And we are done with the first question then. This was quite an easy question. Now we look at the second question. Second question is on geometry. We'll cut this question. We'll crop this question. This is very annoying. I will actually want this picture to be a little larger because there is an image and we can use this actually. Then I won't have to draw any more pictures. Okay, question number 2. What does this say? Question number 2 gives us a circle of radius 6. So this circle has radius 6 and we are given B, C, D and E points on the circle such that B, D and CE, when extended, they meet outside the circle at A. The length of AD is given to be 5. Length of AD is given to be 5. Length of AE is given to be 4. DBC is a right angle. We'll try to draw a straight line here. Good enough. So triangle DBC is a right angle triangle, and we have to show that the length of BC is this number. Instead of that, highlight it. Show that the length of BC is this number. We'll also join this line. We'll try to redraw this line once. Does the job. Okay, so first of all, since this is a right angle, it's easy to see that DC is a diameter. So clearly DC is a diameter, and since DC is a diameter, this angle DEC will also be a right angle because angle in a semicircle, right? So DC is a diameter and angle DEC is 90 degrees. What else? So since angle DEC is 90 degrees, this triangle ADE is a right angle triangle now. And so we apply the Pythagoras theorem in this triangle ADE. By Pythagoras theorem, we know the Pythagorean triplet 3, 4, 5. So DE will just be 3. It's easy to calculate. DE will just be equal to 3. And okay, we were given the radius of this circle to be equal to 6. The radius is equal to 6. So DC, being the diameter, is of length 2 times 6, that is 12. Again, DEC is a right angle triangle. So we apply the Pythagoras theorem again and get EC equal to 3 root 15. If you calculate, this is just root over 12 squared minus 3 squared. This is 144 minus 9. 144 minus 9 is 135, and this is just this value. Okay, so we have this EC also noted down here. Now notice that triangle ADE is similar to triangle AEC. Why exactly? Okay, I will write it down here on this side. Notice angle DAE is equal to angle CAB, because this is just the same angle, right? Again, angle AED is equal to angle ABC, because these are 90-degree angles, so they have to be equal. Both of these are 90 degrees. So by the AA criterion, of similarity, we get that triangle ADE is similar to ADE, similar to ACB. Note the ordering of the vertices in this statement. It's important. Okay, so we have triangle ADE is similar to triangle ACB. So AD over AD over AC is equal to DE over CB. AD by AC is equal to DE over CB. So this is equal to, this implies, now AD is equal to 5, so I put the value 5. AC is 4 plus 3 root 15. This is equal to DE. What is DE? It's 3. And CB, that is what the question wants us to find, or in fact prove. Now you simplify this and you get BC is equal to, just cross multiply, 3 4s are 12, 3 3s are 9 root 15 over 5, and we are done. It's a very simple question, just Pythagoras theorem and similarity. So we are done with the second question also. We move on to the third question. So this is the third question. It's on calculus, just basic derivatives. So we'll see what this question wants. We are given a function f defined on the reals, uh, and this is the definition of the function. So function, the f of 1 is equal to 1, and everywhere else it is this huge expression. Huge expression. We want to find f dashed 1. So we'll just use the definition of a derivative. So this is just part 1, part A. F dashed 1 is equal to limit x tends to 1 f of x minus 1 over x minus 1. This is very important to notice that we just can't directly state that f dash 1 is equal to limit. We are nowhere given that it is differentiable. So f dash 1 will be equal to this limit if it exists, or I should clarify, if the limit exists. So I will also put a small question mark here. So if this limit exists, then I can say that the value of this limit is equal to f dash 1. So we will just, for now, we will focus on this limit. We'll calculate this. Since x is tending to 1, x is not equal to 1. Since x is not equal to 1, we can just use this expression. Limit x tends to 1. What is f of x? E to the x to the 10 minus 1 plus x minus 1 squared sine of 1 by x minus 1. This is f of x minus f of 1. F of 1 is given to be 1. Over x minus 1, right? Okay. We pair this minus 1 with this exponential expression. We'll just rearrange the stuff here. And this is equal to the limit as x tends to 1 e to the x to the 10 minus 1 minus 1 over x minus 1 plus x minus 1 sine of 1 by x minus 1. This whole limit. Straight away, we can't say that the limit of this plus this is equal to the limit of this plus the limit of this. We first have to that exists only when these individual we have ensured that these individual limits exist. So we will show just that. We will show now that these limits, that the individual limits exist. Once we have made sure that the individual limits exist, we can then distribute limit x tends to 1 among these two expressions. So now I will show you a very interesting thing. This is the first limit, right? You can try it the hard way, you can try maybe factoring x to the 10 minus 1 minus 1. You can try it the dirty way. You can do it, you can maybe use L'Hopital's rule, because it, you have to check that it satisfies the conditions for L'Hopital's rule. But if you, there's a smart way. If you look at this expression, take it as a function. Okay, you will very easily notice that this is the definition of the function, the first principle of the definition of the definition of the derivative of this function. This is just I'm sorry, this is just d by dx of e to the x to the 10 minus 1, this function. If you take this as g of x, then this is g of x minus g of 1, because if you put x equals 1, this becomes 1 by x minus 1. So this is just the limit form of the derivative, the first principle. And this is very easily, oh, okay, I'm sorry, derivative at x equal to 1, this is equal to just 10, right? So this is the first limit. Now we look at the second limit. First of all, we'll just use squeeze theorem for this. So sine of 1 by x minus 1, whatever be the value inside these brackets, since we are using the sine function, this has to lie between these limits, right? So x minus 1, sine of 1 by x minus 1 is less than equal to x minus 1 greater than equal to 1 minus x. Now you might ask, how could I multiply x minus 1 throughout these inequalities? It could have been negative, maybe the inequalities would get reversed, but since here in this context I'm talking about x tends to 1, we will ultimately be in a neighborhood of 1 where all of the values are positive. So since, okay, if you look at this number line like this, x is tending to 1 here, we are coming here, since we are getting closer and closer to 1, in these neighborhoods all of the values are positive, right? So we don't need to worry about that. Okay, what did I just say? I think I said something stupid. Oh, I said something very stupid. Please ignore that. Okay. If x is less than 1, this will be negative. If x is greater than 1, this will be positive. So we can't really multiply out by x minus 1. But what we can do is, this tells us the modulus is less than equal to 1, right? So please excuse that stupid mistake of mine. Okay, so now we multiply the modulus of this is less than equal to modulus of x minus 1, right? Now the idea is basically the same. Since I don't want to get into the confusion of the inequalities getting reversed or something, I'm just using modulus. Idea is just the same. We'll use squeeze theorem. Now limit x tends to 1 is equal to 0, and this is a positive quantity or maybe non-negative quantity, and it is getting sandwiched to 0. So this just implies limit x tends to 1, x minus 1 sine of 1 by x minus 1 is equal to 0. So this limit exists as well. So we have shown that in this expression, the limit of this sum exists, this term exists, and the limit of this term exists as well. So we can finally write this as limit x tends to 1 e to the power x to the power 10 minus 1 minus 1 over x minus 1 plus limit x tends to 1. See, now we can write limit x tends to 1 separately for each of these terms, because now we know that the limits exist. So this value we got as 10, this value is 0, it's 10. Therefore, f dashed of 1 is equal to 10. This is our answer for part A, right? Okay, we are done with part A. Now we move on to part B. What does part B say? Go back to the question. We have to evaluate this summit, this limit, right? Okay. We'll write down the limit first. Sorry. Limit as u tends to infinity 100u minus u. I just check it's recording, right? Yeah, sorry for that. Minus u times the summation as k goes from 1 to 100 f of 1 plus k over u. So this was the limit, right? We'll check once again. Yup. So this is the limit we want to evaluate. So the first thing we are going to do is we'll take u common and move this 100 inside this summation. So this will become okay, we'll do this later. We'll write it k goes from 1 to 100, 1 minus f of 1 plus k by u. So this is, and now we rearrange this. We bring this u down here and we multiply and divide by a k. We bring minus k outside and we get limit u tends to infinity summation k goes from 1 to 100 f 1 plus k over u minus 1. What is 1? It's just f of 1 over k by u. This k comes from this k. We multiplied and divided so that we can get a nice expression here. Now you will notice that as u goes to infinity, 1 by u goes to 0. More specifically, k by u goes to 0. So if, okay, I'll erase this. Since we have a finite sum here, we can just bring the limit inside and get this. Since u goes to 0, k by u, u goes to infinity, k by u goes to 0. And therefore, this limit right here is nothing but the derivative of f at 1. If you look closely, you will see this is just the derivative of f at 1. This is minus k times summation as k goes from 1 to 100. Okay, I think I have overused a symbol. Should not have brought this k outside. Okay, I have made another small mistake. This minus sign will be outside, no problem. The k should be inside. We are multiplying and dividing by k inside only. We'll keep this k here. K times f dashed of 1. Okay. K goes from 1 to 100. K times what is f dashed of 1? We calculated it to be 10. This value is minus 10 times 100 times 101 over 2. 50500. This is our third question. We made it length. We spent more time on this than was needed, but okay, we have solved this question now. We'll move on to the fourth question. Okay. Fourth question. Do I have enough space here for fourth question? Then we'll move to the top of the page. So this is a fourth question. It's geometry, calculus, coordinate geometry involving question. We'll see. We have a square S formed by the four vertices 1, 1, minus 1, minus 1. Okay, it will be easier if we just draw it. So we have the square here formed by the four vertices 1, 1, 1, minus 1, minus 1, 1, and minus 1, minus 1. So let the region R. The region R is defined as a set of points inside this square S. The name of this square is S, which are closer to the center than to any of the four sides. So, if this is a point, inside the square S, for it to lie in the region R, it should satisfy that this distance is less than this distance or this distance or this distance or this distance, right? So it is closer, it's closer to the center than to any of the four sides. Okay, so Since the diagram is symmetric in the 4 quadrants, we'll just focus on the first quadrant, and we'll further reduce it by symmetry, but we'll just see it. Okay, we will look at the first quadrant only. That's a straight enough line. Okay, this point right here is 1 comma 1. Okay, so if this is one of those points, this point is closer to the origin than to any of these sides. So in fact, therefore we have these inequalities. What is the distance of this point from the center? It is just x squared plus y squared, the positive square root of that. We are given that this is strictly less than 1 minus x. So if this is x, this is 1 minus x. So this distance is 1 minus x. And we have another inequality. Okay. Notice another symmetry. Notice another symmetry. Even in this diagram, in this square, we divide this square over this line. What is this line? This is the y equal to x. We divide this part of the square as using the y equal to x line. Now, if any point here lies in region R, then the reflection of this point over this y equals x line here will also lie in the region R. In fact, the point I'm trying to get at is that the region, that these two parts of the square are symmetric. That is symmetric with respect to the region R. So instead of focusing on both these parts, both these two triangles, we just focus on this square. We just focus on this right angle triangle. I'm sorry. We will focus on this. So for this point, and why did we break it into two parts? So that now we won't, you will notice, you will remember that I wrote two inequalities here. So if we divide it into two symmetric, divide into two symmetric triangles, we won't have to write two inequalities. It's just a try to make the notation simpler. So this length, now you will notice that this length is 1 by x and this length is 1 by y. Quite clearly, since this point is lying in this right angle triangle, 1 minus y will be less than 1 minus x. So we want this distance of x comma y from the center to be smaller than this, which is already smaller than this. So we don't care about this x anymore. We don't care about this line anymore. We just care about the shorter line, which is a stronger constraint. We want this to be true. So we won't have to deal with two inequalities. Okay, so this is the inequality that we want to work with. Squaring both sides of this gives us x squared plus y squared is less than 1 plus y squared minus 2y and this just gives us the inequality x squared is less than minus 2y plus 1. This is a parabola which opens downwards. So this parabola will look somewhat like this. Okay, so if you put x equal to 0, y will be, so we look at the curve. Okay, we look at the parabola. X squared equals minus 2y plus 1. It should be something like this. We don't need an accurate diagram. Okay. We want this region. So this is the inequality that that all of the points in the region are in this right angle triangle satisfied. So how do I find the area of this region? Integration. So we want to integrate from 0 to this point. Now how do we find out this point? We just solve this curve with y equal to x with this line. So we want to find out the intersection point of the parabola x squared equals minus 2y plus 1 and y equal to x. We just equate y equal to x in this equation of the parabola, and we get x squared equals minus 2x plus 1. Solving this, we will get two values of x, that is minus 1 plus minus root 2. Yeah, minus 1 plus minus root 2. We don't want the negative value, obviously, because we are working in the first quadrant. So we'll just take this value. So x is root 2 minus 1. This point right here, the coordinates of this point are root 2 minus 1 comma root 2 minus 1. So what is this area that we want? This area is, I will do the integration here. So our required area is equal to the integral from 0 to this root 2 minus 1 of this curve, the upper curve minus the lower curve. What is the upper curve? The upper curve is x squared equals minus 2y plus 1. So y is equal to 1 minus x squared over 2 2y 1 minus x squared over 2 minus the lower curve. The lower curve is just x. So this is the integral that we have to calculate. This is just routine calculation. It's nothing to think about here. In order to simplify the calculation, what we can do is x squared minus 2x minus 1 plus 1 right? Okay, So what is the we have to calculate this now. This is half of 2 times root 2 minus 1 minus root 2 minus 1 plus 1, which is just root 2 whole cube over 3. This is our answer. It is root 2 minus 1 minus 2 to the 3 by 2. 2 to the 3 by 2 is just 2 root 2 over 3. 3 root 2 minus 2 root 2 is just root 2 over 3 minus 1. This is our answer. Unless I made some calculation mistake in this last part of the calculation, this answer is correct. This is our final answer. The calculation isn't the main part of the question anyways. Okay. No, wait. I was missing out on a very simple point. The calculation is, I guess, I hope okay. But what is this area? This area is only for this part of the first quadrant. We have another part for the first quadrant. In fact, we have 8 more parts like this. For each of these, we have to calculate the area. So our final answer will be equal to 8 times root 2 over 3 minus 1. I think I have made some mistake. This value comes out to be negative, if I'm not wrong. Okay, yes, I have indeed missed something here. So this is when we put root 2 minus 1. Now what if we put 0? When we put 0 here, this is equal to 0. And when we put 0 here, it's not actually 0. There is a part. That is the thing that I missed. For root 2 and then we put 0, it is minus of 1 over 3. Yes. This value is negative. I'll erase this. So our final answer is 6. 6 root 2 minus 2 root 2, 4 root 2. And minus 6 plus 1 is minus 5. So this is the area of the part of the region R that is in this part of the first quadrant. We have 8 more such symmetric parts. So our final answer will be 8 times 4 root 2 minus 5 over 6. 4 times 4 root 2 minus 1. This is a final answer. So unless I made any other calculation mistake, this is the final answer and we are done. We are done with half of the question paper. We move on to question number 5 now. Question number 5 gives us a function g which takes positive integer inputs and gives us positive integer outputs, and g of n for positive integer n is defined to be the product of the digits of n. That is, suppose we have the positive integer 512, then g of n will return 5 times 1 times 2, which is just 10. So it's just a product of the digits. The first part of the question wants us to prove that g of n is less than equal to n for all positive integers n. Now, for this, assume that n has d digits, and the digits are nd, n sub d minus 1, n2, n1. So this is the number, and nd minus 1, where ni are all digits. That is, more mathematically, ni belongs to 0, 1, 2, all the way till 9, and a further constant, nd is not equal to 0, obviously. So n has d digits. This is just 10 to the power d minus 1 times nd plus all the way till 10 times n2 plus n1, right? So this is our n. For this n, what will be the value of g of n? G of n, remember, is the product of all these digits. So g of n simply will be nd times nd minus 1 all the way till n2 times n1. Now, all of these digits n1, n2, nd minus 1, all of these are less than 10. So this is less than equal to nd times 10 to the d minus 1. So there are d minus 1 numbers here that are multiplied, and each of them is less than 10. So this is what we get. Now notice that this 10 to the d minus 1 times nd is this part. So this is definitely less than 10 to the power d minus 1 times nd plus all the way till 10 times n2 plus n1. This is just n. Therefore, g of n is less than equal to n. Now you might ask, when is equality achieved? Very simply, for single digit numbers, 1, 2, or all the way till 9, for each of these numbers, g returns, since they have only one digit in their number, the product of the digits is just that digit. So g gives 1, 2, all the way till 9, right? So the first part of the question is done. Now we move on to the second part, b. What does b want? We have to find, the part b asks us to find all positive integers n for which n squared minus 12n plus 36 is equal to g of n. we have to find all. Let n be a natural number such that n squared minus 12n plus 36 is equal to g of n. Now we use part A. In part A, we have proved that g of n is less than equal to n. This implies n squared minus 13n plus 36 is less than equal to 0. Factorizing this, we get n minus 4 times n minus 9 is less than equal to 0. Therefore, n must belong to 4, 5, 6, 7, 8, 9. N belongs to this set. Now, all of the elements of this set are single digit numbers, and we just discussed single digit numbers when given as input to G give that number back. So G of n is equal to n for whenever n is a single digit number. So for each of these numbers, equality is achieved here. So this inequality turns to equality, and we get that n equals 4 and 9 are the only solutions. So question number 5 is done. It was a fairly simple question. Now we move on to the 6th question, another number theory. Question number 5 is a number theory question. Question number 6 is again a number theory question. In this question, we are given prime numbers P1, P2, P3. With P2 is not equal to P3, and we are given that 4 plus P1, P2 and 4 plus P1, P3 are perfect squares. We have to find all possible values of P1, P2, P3. Assume that 4 plus P1, P2 is equal to a squared, and 4 plus P1, P3 is equal to b squared for some positive integers a and b. Okay, since P2 is not equal to P3, and so a is not equal to b, obviously. Without loss of generality, let us assume that P2 is strictly less than P3. Since the question is symmetric about P2 and P3, we can take P2 less than P3, you can take P3 less than P2, doesn't really matter. I'm showing this so that we have some ease in our notations. So since P2 is less than P3, this is less than this, and A is less than B. This is what we get. Now, P1, P2 is equal to A squared minus 4. This is equal to A plus 2 times A minus 2. This is P1, P2. Since P1 and P2 are primes, either the only possibilities are that P1 is equal to A plus 2 and P2 is equal to A minus 2, or P1 is equal to A minus 2 and P2 is equal to A plus 2. It doesn't really matter which one we go with without loss of generality. Assume P1 is equal to A plus 2, and therefore P2 becomes A minus 2. Now similar with this gives us P1 P3 equals B squared minus 4. This is B plus 2 times B minus 2, and again by the same argument, P1 and P3, either P1 is equal to B plus 2 and P3 is equal to B minus 2, or P1 is equal to B minus 2 and P3 is equal to B plus 2. But since we have fixed P1 and P2 here, since P1 we have assumed without loss of generality to be P1 equal to A plus 2, if we take P1 equals B plus 2, using this and this, we will get A is equal to B, but we have assumed this, A is less than B. So that can't be. So P1 has to be equal to B minus 2 in this part, and therefore P3 will be B plus 2. Okay. Now P1 is equal to A plus 2 is equal to B minus 2, implies B is equal to A plus 4, right? Now again we rewrite some stuff. We have P1 equal to A plus 2. We will basically write everything of B in terms of A. What is P2? P2 is A minus 2, and P3 being B minus 2 and B being A plus 4, so P3 will become okay, P1 is A plus 2, P2 will become A minus 2, again P1 will be B minus 2 here, right? B minus 2. P3 is B plus 2. Okay. Oh, this is P1. Why am I getting confused? P3 here is B plus 2. A plus 6. So notice that these three values, A minus 2, A plus 2 and A plus 6, this forms an AP with common difference 4. So P2, P1, P3, these three prime numbers, P2 being equal to A minus 2, P1 being equal to A plus 2, and P3 being equal to A plus 6, this forms an AP with common difference equal to 4. So this is a prime AP, right? Now let, if possible, we don't know if it is possible yet, but if it is possible, assume that P2 is greater than 3, that P2 is some prime that is greater than 3, 5, 7, anything. And we know that primes greater than 3 are plus or minus 1 modulo 6, correct? So first case is P2 is congruent to 1 mod 6. If P2 is congruent to 1 mod 6, P1 being the next term in the AP. We will highlight the AP here. P1 being the next term in the AP, P2 plus 4 is congruent to 1 plus 4 congruent to minus 1 mod 6. And the next term is P3, which is equal to P1 plus 4, and this is congruent to 4 minus 1 congruent to 3 mod 6. Now a prime number greater than 3 can't be equal to 3 mod 6. This is a contradiction. We shouldn't say contradiction. This is not possible. Correct? So we move on to the second case, where P2 is congruent to minus 1 mod 6. If P2 is congruent to minus 1 mod 6, we get P1 equal to P2 plus 4 congruent to 3 mod 6. So the argument breaks here only. A prime greater than 3 can't be 3 mod 6. It's not a prime at all. It's divisible by 3. So this is not possible. Therefore, P2 can't be greater than 3. Therefore, P2 is not greater than 3. So P2 is less than 3. Less than or equal to 3. So what are the possible values for P2? So P2 is a prime which is less than or equal to 3. So P2 can be either 2 or 3. Now, very clearly, if P2 is 2, what is P1? It's P2 plus 4, an even number plus an even number. It's no longer a prime. So P2 can't be equal to 2. Therefore, P2 must be equal to 3. And then we get P1 equal to 3 plus 4 equal to 7, which is again a prime, luckily. And P3 is P1 plus 4 equals 7 plus 4 equal to 11. So this is a prime again. So the only possible values of P1, P2, P3 are P1 is equal to 7, P2 is equal to 3, and P3 is equal to 11. This is our answer. We're done with the 6th question as well. Move on to the 7th question. The 7th question gives us a set A. Gives us a set A, one containing all positive integers from 1 to n. And for a permutation P, we are given some conditions. P is a permutation of the set A, and P of 1 denotes the first element of P, right? So we have to find all such permutations P such that for all I and j belonging to A, what are the conditions that we want? I less than j less than P of 1 implies j appears before I in P, and P of 1 less than I less than j implies I appears before j in P. Correct? So our permutation P has to satisfy both of these conditions. Now, suppose P of 1 is equal to k, any k. There are n choices for there are n choices for P of 1, right? Now when we have fixed P of 1 equal to K, we define two sets, A, L. L be the set of numbers from 1, 2, 3 all the way till K minus 1, and we find AR as the set K plus 1, K plus 2 all the way till N. So these are the two sets. That is, A is just all of the elements in A that are to the left of P of 1, that is K, and AR are the elements that are to the right of P of 1 equal to K. Now, according to this condition, set of conditions that the question says, if I is less than J, I less than J less than P of 1, all of these elements in AL are less than P of 1. So for any I less than J in A of L, in A sub L, J appears before I in P, in the permutation P. Basically, AL is, how should I say it? AL appears in the descending order in P. Wherever it appears in P, it will all of these elements of AL will appear in the descending order. And for any I less than J and I is greater than P of 1 in A sub R, the order is retained, that is I appears before J. So this just appears in ascending order, appears in the natural ordering only. So now, how do we create the permutation? P of 1 has already been chosen in n ways, right? Has already been chosen in n ways, and now for each of these n ways we have to select k minus 1 of the p of i's and assign them to the values in A L in the descending order. So we have to choose k minus 1 positive integers I1 less than I2 less than equal to n greater than equal to 2, such that P of I sub k minus 1 is equal to 1, P of I sub k minus 2 is equal to 2. That is in the descending order. P of I sub 1 is equal to k minus 1. Okay. So how do I choose these k minus 1 positive integers from these n minus 1 positive integers? It's simply n minus 1 choose k minus 1. N minus 1 choose k minus 1 base. Now, once both of these tasks are done, this is done, we are left with still how many? We are still left with n minus k positions in P that are still unassigned. How do we assign them? There is only one way to assign them. We have n minus k P of i's and we have n minus k elements in A sub R. They all appear in the natural ascending order. So that can be done in only one way. Or instead of R assigned, say, can be assigned in one way. So for each of these k's, the number of ways in which we can form the permutation is n minus 1, c k minus 1. So our final answer is n minus 1, choose k minus 1. This is for just 1k. Now, as we take k from 1 to n, this is our final answer. And this, as we all know, is just 2 to the power n minus 1. This is our final answer. This was a very simple question on combinatorics. So, question number 7 is also done. Move on to question number 8. I will cut question number 8 in two parts because the question is big. This is question number 8, and we are on to the last question of the paper. So we have positive integers k and k, n, and r. Oh, it's 310. We have positive integers k, n, and r, and we have the polynomial q of x as given with real coefficients. We have to show that q of x over x to the power k is strictly positive for all real x satisfying a constraint. Our polynomial q of x, okay, this is part A. Our polynomial q of x is x to the power k plus a1 k plus a sub n x to the power k plus n, or taking x to the power k common, it's just 1 plus a1x plus all the way till an x to the power n. One plus a1x we need this condition now because we have moved x to the power k to the denominator, and this is actually not something we need to worry about because the constant that we have been given tells us that mod of x is strictly greater than 0. So x can't be equal to 0, right? Now, what is the range of values that we have? X satisfies this. One plus summation mod ai as I goes from 1 to n. Is that correct? Okay. Very easily you can notice that this is less than 1. Okay. Now, mod of a1x, we look at this value, an x to the power n, which is basically this q of x by x to the power k minus 1. This is less than equal to mod of a1 mod of x, simple triangle inequality, mod of a2 mod of x squared all the way till mod of n mod of x to the power n. Since mod of x is less than 1, x to the power mod of x to the power n will be less than mod of x to the power n minus 1. All, in fact, all of this thing is less than equal to mod of a1 mod of x, mod of a2, again mod of x, because mod of x square is less than mod of x, because mod of x is less than 1. Mod of x. As I goes from 1 to n, mod of x. Correct? So since mod of this, I'll just rewrite is less than equal to summation as I goes from 1 to n mod of ai mod x. Therefore a1x plus all the way till a sub n x to the power n is greater than equal to minus as x summation as I goes from 1 to n mod of ai times mod of x. Now we just add 1 to both sides. Now the left hand side is just q of x over x to the power k. This is equal to 1 minus summation I equals 1 to n mod I mod x. Now we have been given that mod x is less than 1 by 1 plus summation mod I mod ai. So this will be greater than 1 minus summation as I goes from 1 to n mod ai times 1 over 1 plus summation as I goes from 1 to n mod ai. This is 1 plus summation I goes from 1 to n mod ai, and this is strictly positive. So q of x by x to the power k is strictly positive. This is what the question demanded. Strictly positive in this range. Correct? So the first part of question number 8 is done. We'll move to the second part. Cut this also. This is the second part of the question. We now have a polynomial p of x. It's a non-zero polynomial with real coefficients, and m is given to be the smallest number such that the coefficient bm is not equal to 0. That is, all of the coefficients b0, b1, all the way till bm minus 1 are equal to 0. So basically, the polynomial is just p of x equals bm x to the power m is bm plus 1 x to the power m plus 1 br x to the power r. Correct? We take x to the power m common, and that gives us bm plus bm plus 1 x till br x to the power r minus m. This is starting to look a lot like the previous question. Okay, now look at this. look at this part. This part is nothing but that q of x by x to the power k from the previous part, right? So this part, bm plus 1x plus all the way to br x to the power r minus m, this polynomial is strictly positive in a given neighborhood of x, correct? To be more precise, bm wait till br x to the power r minus m is strictly positive for all x such that mod of x is greater than 0, strictly less than 1 by 1 plus summation bi as I goes from m to r. This is by part A, correct? So in this interval, in this neighborhood of 0, this polynomial is always strictly positive. So the sign of p depends on only this, only on x to the power m. Now, because that is what the question wants. The question wants us to prove that the graph of y equals p of x cuts the x-axis at the origin if and only if m is an odd integer. And what does it mean by cuts the x-axis at the origin? It means that p changes sign at x equal to 0. That is, to the right of x equal to 0, p is positive, and to the left of 0, p is negative, or to the left of 0, p is positive, and to the right of 0, p is negative. That is, p changes sign. Now, this part is always positive. So the changing of sign is all up to x to the power m now. If m is even, then for any h negative p of h, okay, for any h positive, p of minus h will just be minus h to the power m times some positive quantity, and since m is even, it will just become h to the power m times the positive quantity, and this is positive since h is positive, and p of h is just h to the power m times a positive quantity, and this is again strictly positive. So to the both sides of 0, p is positive. P is not changing sign when m is even. Now let us look at the case where m is odd. If m is odd, for any h positive, p of minus h is minus h to the power m times a positive quantity, okay. There is a small correction to make. Say now, since we want to use the property that this value is greater than 0, we have to work in this neighborhood only. So we call this neighborhood as I. Okay, so for all h positive in I, so that we don't go out of that range, so that we still can use this positive quantity thing. Okay, Now, that was a digression. So now p of minus x minus h is minus h to the power m times a positive quantity. And since m is odd now, this just becomes minus h to the power m times a positive quantity, which is negative. And p of h is just h to the power m times a positive quantity. Since h is positive, this is positive. So to the left of 0, p is negative, and to the right of 0, p is positive. Therefore, p changes sign. And we are done. Therefore, p changes sign if and only changes sign at 0 if and only if m is odd. And that brings us to the end of the question paper. This was a rather easy question paper only. The questions were interesting. I would say the geometry was easy. I would say especially these two number theory questions were the interesting ones in this paper. And I also liked this question on polynomials. So yeah. So that was it for this discussion. We will meet in the next video. So until then, bye bye.